Okay, we're going to try to do this one here. We have a perfume bottle full of perfume, and the density is about the same as water. And then Pete gives you some information about this situation. We have this bulb here that's 50 centimeters cubed, and it is connected to this tube. It narrows to a diameter of 2 millimeters, and when he squeezes the bulb within 1 second, I squeeze the bulb, let's see, the perfume gets pulled up. The perfume down here gets pulled up into this area and is misted out here. If I completely compress the bulb in 1 second, find the velocity of the air in the thin part of the tube. So presumably that's the velocity right here, if the compression of this takes 1 second. Okay, so I think the second part of the problem asks for some other calculation, but I wanted to introduce this equation because it's going to involve this equation. Well, you know it already. It's the Bernoulli relationship. And what I wanted to say is that this relationship is nothing more than basically the conservation of energy. And let's see. Conservation of energy. So what it's saying is that the energy before equals the energy after. Before in the fluid equals the energy after. So for example, if you have a fluid that is traveling in some sort of tube and it has some initial velocity v1 and some initial pressure p1, and that flows through the tube, and notice it's at a height y1, okay, y being this axis. If it gains potential energy here, that's going to be reflected in this term right here, y2. It will also, if it has a different velocity, v2, and a different pressure, v2, p2, when you add all these up on this side and these up on this side, they have to be equal. So what's happened is, you can imagine if you have this very small area and you have a particular velocity and you go to a large area, your velocity is going to drop. And likewise, if you have a initial pressure, and by the way, this is essentially the static pressure. So the static pressure, and this is considered the dynamic pressure. So if you had, in this case, we start out with a static pressure of, pretty much atmospheric pressure. We've got this, air in the bulb. It's at atmospheric pressure. And what we're going to do is we're going to accelerate that through this by squeezing this bulb, or accelerate through there, and it's going to give up this static pressure to create a dynamic pressure on this side. So what is the velocity of the air in the thin part of the tube? So, well, what we know is it in 50 centimeters cubed per 1 second is the rate of the volumetric rate of flow, which is equal to the velocity times the area. The velocity is going to be centimeters per second times the area, centimeters squared, of this orifice as it passes through here. So let's go ahead and do that. Okay, we have that 50 centimeters cubed per 1 second equals the velocity times the area, and we know this is it's an orifice that has a 2 millimeter diameter, so the area, the pi r squared, equals pi times the diameter r is its diameter equals 2 millimeters, so r is 1 millimeter, 0.1, I'm going to try to match centimeters squared. So the velocity equals 50 centimeters cubed per second times 1 over pi 0.1 squared, centimeters squared, equals 50 over 0.1 squared is 0.01. 0.01 pi centimeters. We've got centimeters squared here. It cancels with this, so that we get centimeters per second, or 5,000. See, 5, move that 2 zeros, move 2 zeros, move 2 zeros. 5,000 over pi centimeters per second is the velocity, which is roughly, I don't know, 5 divided by 3.14 is probably 1.53, 1.5 roughly, 1500 centimeters per second is the velocity. Wow, that is fast. Whoo! That is the velocity in the thin part of the perfume bottle.